Hello everyone. Today we have Dr. Andrew Gelman, who's a professor of statistics and political science at Columbia University. He does a lot of work in Bayesian data analysis, Bayesian statistics, does a lot of research in like polling data and that stuff related to like political science. If you ever take a Bayesian statistics class, it's very likely that you'll be reading one of his textbooks. So without further ado, the floor is yours.
Oh, okay. Well, great to meet you all. I thought okay. What I wanted to talk about was Bayesian workflow, and by which I guess what I mean is that when we do statistics or data analysis at any level, which means you might be working for a newspaper and you're looking at a government report and trying to assess their claims. You might be working for a company and you've hired a contractor and the contractor wrote a report and then you want to gather some data and figure out what to do. You could be a political candidate and you do a survey and you want to find out who in the city supports you and who has never heard of you and what you should do. That when we gather and analyze data, we're acting as scientists. And now I don't just mean like, okay, gathering data is an important part of science. I mean that we form mini hypotheses. So when I say science, I mean what you think about science, what you learned in fourth grade. You form a hypothesis. I conjecture that if I water the plant more, then it will grow higher. And then I'm going to do an experiment where I have 5 plots. I have 5 pots, and each one I put in some seeds and I give them different amounts of water. And then I'm going to make a graph at the end. And I hypothesize that there's going to be more grow. If I give no water, it won't grow. And there's some threshold of which it will flower. And then if I give too much water, that won't work either. And so here's a little picture of what I expect to see. And now I'm going to gather data. Okay, so when I'm doing statistics, I have hypotheses like I hypothesize that my sample size is large enough that I can estimate the effect I care about confidently. I hypothesize that if I fit this logistic regression model using this computer package, it won't blow up. I hypothesize that if I make this graph that I'm planning to make, I hypothesize I'm not going to see anything very exciting, but I hypothesize I'm going to see an increasing pattern, which is what I thought I would see. We do this all the time, sometimes formally and sometimes informally, but we're always kind of experimenting, and I don't think that's conveyed in statistics textbooks, including my own. It's kind of the way a statistics textbook is usually written, or a statistics paper or a science paper is, here's the conclusion and everything builds to it, right? It's like, it's like the Bible, right? It all builds up to Jesus and everything's about Jesus. Even the stuff that's not about Jesus, you can interpret as being about Jesus. That's the culmination. But that's how we write stuff, but it's not how we do stuff or not how we should do stuff. No, unfortunately, people read books like mine and they do it wrong. They do what we say rather than what we do. So to flip the usual adage. So I'm going to kind of give some examples of that, of how we form mini hypotheses and how we learn. The term workflow is something that's become popular in engineering, especially software engineering, in the past 20 years or so. And to me, it goes as follows. We start with examples. An example is like, I did some analysis. Then there's a case study. A case study is an example where you very clearly lay out all the steps that you did. Then there's a workflow, which is a series of steps which could apply to other problems. Then you have an actual algorithm, which is something that is already programmed that you can feed data into. And then finally, you might have actual theoretical results. And in statistics textbooks, there's a lot of examples, and there's a lot of algorithms and some theorems, but not a lot of workflows. I think there's not a lot of this intermediate step. And you'll see this if you ever try to do something yourself. If you have a homework problem or a term project or you're working a research project, the first thing you always want to do is find out an example of analysis that someone already did that you can copy. But what does that mean? Better than having an analysis you can imitate is having a workflow. So this is our aim. Okay, here's an example. This was from Social Security database. It's just a fun graph, like it's amusing.
Are you
Oh,
sharing?
I was going to share my slide. I have a few slides for you. Yeah, let me share. Thank you. Okay, more. Share. Share. Okay, now I am going to share this. Okay, you see it.
Yep, yep.
Okay, this is from the Social Security database. It's fun. Like you can try to think about like what names end in D and E and so forth. Um, it's kind of silly because it's originally the data, but you can like think about what these like, John ends in A and William ends in M and Michael ends in L and so forth. So here's the distribution. 50 years later, well, this is another distribution. Now there's a lot of Y's because it was an informal time in the 50s. People gave their kids names like Larry and Billy. These are their actual official names, not just what they were called. And now I'm going to show you something which is very stunning, which is from 2006. I want you to form here, I'm going to show you these two again. Here's 1906. Okay, you can look at for a second. Then I'm going to show you 1956. Really, it's better to show them at the same time. I'll do that. I want you to just, in your head, form a hypothesis about what it's going to look like in 2006. Just a, little hypothesis. I'm going to give you, are people in a room like they can talk to each other?
Yeah, they can talk. Yeah.
Talk to your neighbor for 30 seconds about what you think it's going to look like.
I think the graph height is almost at the new place in both the timelines. So I think it will be similar to that that's in the at 2006 it's like the same.
Okay, so I'll show you. What the hell? Okay, this is my nomination for this was made by someone named Laura Wattenberg. I mean, I read you the graph, but it's my nomination for one of the greatest graphs based on data in plain sight that nobody had looked at before. Okay, well we can string them together. It's kind of hard to read now with the three, but you can see how things changed from from this 50-year period. Very dramatic. Now, my point here is that we got something out of talking about our expectations. We don't always have to do it. You could do it in the other order. The reverse order would be you see the graphs and then you say, well, that third graph looks really weird. It's like looks very surprising. It looks like someone's like flipping you the bird or something. It's striking. And when you see something surprising, then you should think about what's surprising about it. What were your implicit assumptions? What was your model for what was going on? There's a term in statistics you probably heard, exploratory data analysis, which you might associate with making graphs. Right? Well, exploratory data analysis is said to be the procedure where you look at data to find the unexpected. Right. So it's different than like I have a graph, like the usual graph would be I have something and I want to show it to people. And so here's like, I'm going to like shove it in your face. Exploration is I make a graph ready to be surprised. But if that's true, then that means that the unexpected is relative to the expected. So what that means is if you're going to do exploratory data analysis, it's good for you to have a model. And if it's not an explicit model, it's an implicit model. So one thing I like to say is that if we can interrogate our assumptions, we can understand our implicit models. Now, what's going on here? I think the theory is that there are trends based on the sounds of the names and how the word ends, how the name ends somehow seems to be more relevant to people. There are other ways of graphing these data. So I have the last letters of boys' names. So this is a graph with 26 lines. And it's tricky to think how to display them. So what I did was I chose three, D, Y, and N. D, I guess, was like a lot of Davids. And N is all those names like Jaden and Jalen and Brandon and Bowen and so forth. I don't know what's been happening since 2006, but it's still high. Very striking, like things changed a lot after 1950. What else changed after 1950? So the other graph we made is the total popularity of the top 10 names for each year. As of in the late 1800s, more than 40% of boys were given the top 10 names and 20% of girls. And then it was pretty steady until about 1950. Since 1950, there's been this growing individualism. And now boys' names are as trendy as girls' names. And that didn't used to be the case. So these things all go together. This is an example of how we in a very simple case of how we're being like little baby scientists here. But again, I'm not just saying I'm being a scientist and gathering data. I'm saying I'm making hypotheses about what these data mean. So I'll give you another example. I have a little bit of a big picture first, so I wanted to tell you. The three challenges of statistics, as I see them, are generalizing from sample to population, generalizing from treated to control group, and generalizing from observed data to underlying constructs of interest. And let me explain why they're all challenges, especially with what we call big data. So big data are not random samples. Typically, they're available data. Big data typically are not randomized experiments or assigned treatments. They're exposures. And big data are whatever data you don't get to measure exactly what you want. So the role of statistics is to draw a connection between the data we have and the questions we want to answer. And that's always the case, even in cases that seem very clean. So in your classes, they may use examples of medical experiments. That's considered to be the cleanest type of study. You randomly give half the people the treatment, half the people the control. You measure them before, you measure them after, you look at how much changes there have been in the two groups, and you compare them. And that's considered to be the most kosher analysis. Well, it's not completely clean. I'll tell you this because real life medical experiments are done, they're contracted out to companies that do clinical trials, and the companies that do clinical trials are motivated to get success. And the best way to get success is that if somebody is in the control group and they start getting better, then you find a reason to kick them out of the study. Like they showed up 10 minutes late to the appointment, so you kick them out. And if they're in the treatment group and they're getting better, then you just keep calling them up, like, come into the study, so forth. So there's bias even there. You can estimate such things. But setting that aside, even without that, the goal of the medical trial is not to say how effective is this drug on the people in the study. It's supposed to be how effective is it in the general population. And drugs are never tested on a random sample of people. I mean, of course not. They're not going to give you, they're only going to give you the drug if they think you might benefit from it. Once the drug is released, all sorts of people will use it. So it will tend to be less effective in the wild than in the experiment. That's the kind of thing that you have to think about. Now, I wrote this interlocking logic thing. Okay, what do I mean by that? I'll just say each thing. So inquiry is your question, what you want to learn. The data are what you have available. The statistical model connects those. What does regularization mean? We learn about the people in the study at the time of the study. We want to extrapolate to other people in other times. So the way you do that is you model, let's suppose, I will model the response based on individual and situational characteristics. So if the treatment's more effective among men than women, or older people than younger people, I want to know that for my extrapolation. If my treatment is more effective during the day or at night or in weekdays and weekends, that sounds sort of silly, right? But think about a political treatment like political ad. That's said to be most effective right before the election because people forget it. But if you do too many ads right before the election, then they kind of cancel each other out. They overwhelm people. So there's an interesting decision problem of when to do the advertisement and what are all the effects. So you would want to model the effect as depending on time as well as other things. So what that means is you're building what's essentially a regression model. You're building a statistical model to predict the outcome given many factors characterizing the person in the situation. If you run a regression and you have a lot of predictors, you get a very noisy estimate. You won't get great prediction. So one thing we know about from machine learning is something called regularization, which is that we get more stable predictions by we don't just fit to the data. So the goal is not to optimize the fit on the training data. The goal is to optimize the fit on the test data. We work on that. So that's part of the logic. Post-stratification refers to the idea of generalizing to the population. And then we have computing challenges, which I'm not going to talk about. I did want to talk about 16 with you for a minute. Can you see me or only see the slides?
We can see you.
Okay, so I just want to talk about 16 because it's one of my favorite statistics numbers. It's that you need 16 times the sample size to estimate an interaction than to estimate a main effect. Now, do you know what an interaction is? You know this jargon?
No.
Okay, then I'll tell you.
Your
It's
hands.
important. It's important. Okay, so you understand by estimating an effect, right? What's the effect of the treatment on a person? An interaction is how the effect varies. So an example of an interaction would be this political ad is more effective for men than for women. So to estimate a main effect, you do an experiment. Half the people get the treatment, half the people get the control. You take the difference and you have a standard error. And the standard error is the square root of sigma squared over n over 2 plus sigma squared over n over 2. It's you divide it into two groups, so n over 2 people in each group. So your standard error, square root of sigma squared over n over 2 plus sigma squared over n over 2. If I want to estimate interaction, that's the treatment effect among men minus the treatment effect among women. It's the difference between them. So that's estimated with standard error square root of sigma squared over n over 4 plus sigma squared over n over 4 plus sigma squared over n over 4 plus sigma squared over n over 4. Because your estimate is not A minus B. It's A minus B among men minus A minus B among women. So it's this minus this minus this plus this. Each one is half the sample size. You now have 4 terms. Each one is half the sample size. So 4 terms instead of 2 is a factor of 2. Half the sample size means that each of those 1 over sigma squared over n over 4 is twice as much as sigma squared over n over 2. So the standard error of an interaction, estimated interaction, is the square root of 4 times, there's a square root of 4 in there because it's 4 terms instead of 2 and this factor of 2, and then you take the square root. So the interaction is estimated with twice the standard error as the main effect. Now, also, interactions are typically smaller than main effects. So typically, you'll have a treatment might be more effective among one group than another, but it's typically like effective among both or not effective among either. An interaction could be half the size of the main effect. If the interaction's half the size of the main effect and has twice the standard error, then that means it's estimated with 1/4 of the precision. But then, as you might remember, you need to increase the precision goes, how accurately you can estimate something goes like the square root of the sample size. So you need 16 times the sample size to estimate an interaction as a main effect. What that means is that you can design a study to estimate an effect, but it's going to be any estimates of how the effect might vary are going to be very noisy. But that's too bad because when you do a treatment, you're not only interested in whether to do it, you're also interested in like how big the treatment should be. And how big the treatment should be is essentially an interaction because you're comparing how effective a treatment would be at one dose versus another. So what that means is that we can never escape our models. Even if we have enough data to estimate a clean effect of the sort that you'll see in your statistics textbook, that's still not enough, because knowing that the drug works isn't enough. You still need to define the dose. Okay, I have a couple more examples, and you all have to tell me when to stop, or like, I don't know, how much time do I have left?
You have about 35 minutes left until 1:45.
Okay, well, we'll see if I take 35 minutes or not, but okay. Okay, here. Okay, I got a story for you, and I was contacted a few years ago by some people who work for Wikipedia, and they were, can you help us like on our statistical analysis? Oh, sure, you're Wikipedia. I wanted to help them. They had, do you know that nag screen in Wikipedia? If please give us $3. If only 1% of people gave us $3, we would support ourselves. So they have the nag screen and they want to make it more effective. So they do what's called A/B tests. They do little randomized experiments, changing how they frame the nag screen, what they say, to see if they can increase the rate of giving. And so, sure, I'm happy to help them. I use Wikipedia all the time, right? So so they told me this, that they did an experiment, and it was changing the nag screen by changing it from having round corners to square corners, which, like, you can look at the windows on your laptop. I assume right now half of you are reading your email, so you can look at the windows on your laptops and you can see that they might have round or square corners. You don't really notice. They didn't think this would have any effect, but it's free to do experimentation because it's an online platform. This is why all these tech companies do A/B tests all the time. They're sending you the nag screen. It's free for them to randomly do either square or round corners. So if they can do it for free, they can do a little experiment. So they did an experiment one day, and you can see it was a couple million people, and about half got square corners and half got round corners. And they found that the treatment decreased contribution rates by 15%. It went from 0.51% to 0.43%. So a decrease of 15% in contributions. And they were a little suspicious. How could that be, that this corner thing? And they said sometimes this happens. They get these really large effects that they don't really believe. And they knew that I had done research on implausibly large effects. So they wanted to know if I had any insight into this. So I looked, okay, so the first thing is, going 15% is a large effect. So I said, well, maybe could it be like the effect varies from day to day? So maybe one day there was an effect of 15%. Maybe it was plus 20% the next day. Maybe it's higher, and the effect is higher in the day than the night, all sorts of things like that. Like, could it just be that, yeah, you found a 15% effect, but that only applied to the day that you did it? And they said, well, they didn't think so, because they said that there is evidence that effects vary, that there's like contribution rates are higher during, sorry, how do you say this? That the rate of contribution varies. Like they said, for example, people who go on Wikipedia during the day are more likely to contribute than people going at night. Like presumably they're different people. But they said that when they estimate treatment effects, different days, different times of day, they seem to be pretty stable. So they didn't think that was the case. Then my next thought was, well, maybe it's just noise. So you see they have a 95% interval, which is from minus 19% to minus 11%. So I thought maybe they computed the 95% interval wrong, but I did the calculation. And indeed, with 2 million people, you can estimate it very accurately. So it's like 10 standard errors away from zero. There's no way this could occur from chance. Because then their next question was, could it just be selection? Could it be that we've tried so many things that just by luck we found a big effect? And I said, just by luck, you can find something that's 2 or 3 standard errors away from zero, but you're never going to find something 10 or 15 standard errors away from zero just by luck. This could not happen. So I stared and stared at this, and then I figured out what went wrong. So what I want you and your neighbor to spend a minute discussing this quietly. No, it's not a group discussion where one person shouts or all, but in pairs, talk to your neighbor and try to look at this and try to figure out what went wrong. I'll give you a minute. So did anyone figure it out?
Anybody have any ideas of what it might be?
Problems with internal browser.
What?
He said problems with internal browsers.
Okay. There's information on this display that made me realize what was going wrong. Okay, I'll tell you. Look at the number of trials. Okay, it's imbalanced. So it's not exactly a million each. And you say, well, they're randomly assigning it. But if you're randomly assigning it with 50-50 probability, it's going to be very close to 50% each because it's a very large sample size. I can do a very quick calculation or even a simulation, and you'd see that you should not get 950,000 in one and 1.08 million in the other. It's too variable for that. Well, if this was a ratio of 2-to-1 or 3-to-1 or 10-to-1, I would think it would be the design, but how could the design be that? So I asked them, I said, why are they unequal? What was the design? They said, no, they're supposed to be randomly giving them to the two things. So let's see what happened. Just in case you're curious, these are the round and square corners. So I'm going to show you here. This is the number of, the experiment was done for 12 hours, roughly, and they have the number of people who got the treatment and the control in every minute. And first the experiment turns on and you can see they're giving it equally. Something went wrong. And I don't know why, but then they were giving a lot less controls than treatments. Yeah, I don't know the story, but you notice that they're giving more, the square corners are happening more in the middle of the night. And remember how I said there's less, remember how I said that people contribute less in the middle of the night? So this is an artifact of the data, which we learned by looking into it. So just kind of an interesting example of how you can figure things out and just how we make these informal hypotheses and go from there. So yeah, there's just nothing with the square corners. It's not a real thing. Okay, I have another example. This was, you probably haven't heard of this one, so I'm not going to do it. I'm going to give you okay. I want to tell you now about, because I think graphics are very important. I think that when statisticians, when we make graphs, we tend not to realize how abstract they are. And I have this new thing now that I like to do, which is whenever I make a graph, I like to build up to it. So rather than starting with a scatter plot, I like to, so like a scatter plot, consider a scatter plot. You all know what that is, right? So that's very, it's like, what could be simpler? Y versus X, a dot represents a person or an item. But if you think about it, it is very abstract because unless these are actually people like in a city on a map, the X and Y axes are not physical dimensions. And I think these things can be hard for people to read. Indeed, the scatter plot, here's another one for you, okay? I'm going to ask you how many I'm going to tell you that that the scatter plot was invented 2,000 years after calculus was invented. So calculus was invented by Archimedes and before, in BC, and the scatter plot was invented pretty much in the 1800s or the 1700s. So even though it's very simple, it's not intuitive. So I want to give an example of how we can build up from simplicity. This is a graph of, it's a basketball. It's someone who's 1.7 meters tall, shooting the ball at the basketball hoop. A basketball hoop is 3.05 meters tall, and I'm going to assume that the shooter is 10 meters away from the hoop. So this is the setup, or you don't have to be 1.7 meters tall, but you're shooting it from that distance off the ground. Okay, I'm going to draw a trajectory of a basketball now. Okay. So on the left is the simplest possible graph you could do. I'm shooting a basketball at a 30-degree angle at 15 meters per second. I'm ignoring spinning and air resistance and all that. As you see, when I shoot that, it goes too high, so it doesn't go into the basket. I can consider different trajectories. Sorry, the same angle, but different. If I throw it at different speeds, I get different trajectories. So you can see if I throw it at 20 meters per second, it goes way too high. If I throw it at 10, it's too low. If I throw it at 5, then it hits the ground and doesn't even get far enough. Now, where I'm going to build up, I'm building up to a graph that's going to tell you what angle you should shoot the ball at and how hard you should throw it to have your best chance of getting the ball going to the hoop. But rather than giving the answer, I want to build up to it. So the only thing that could make this graph more intuitive would be if it was animated, right? But you can see what's happening. So if you're shooting a 30-degree angle, what speed do you have to throw it so it'll go into the basket? Well, that's a simple equation we can solve mathematically. And here it is. The solution is if you throw it at 12.2 meters per second, it will hit. Again, treating the ball as a point and ignoring the backboard and so forth. So I'm using a different color for this. Now that I've solved this, I can look at the solution as a function of the angle. So that's the next step. And that's the graph on the left. So what I had before was the angle at 30 degrees. So if you shoot at 30 degrees, the velocity you need is 12 point whatever meters per second. If you throw it, the dotted line represents, if you're 1.7 shooting for 1.7 meters, the dotted line represents the angle that you have to shoot higher than. If you shoot an angle lower than this dotted angle, the ball will never have a chance. It's too low and it will never have a chance to reach because of gravity. If you shoot at 90 degrees, approaching a 90-degree angle, you have to throw the ball really hard to go really high and then go back in. There's an optimum. The optimum would be the angle for which the required velocity is the minimum. Now, and here it's 10.6 meters per second. It's 48.8 degrees. The next step is I can figure this out as a function of my distance from the hoop. So now that's the graph on the left. So as my distance from the hoop increases, I need a lower and lower angle. The optimal angle is lower and lower, and I have to shoot it higher and harder, throw it harder and harder. That makes sense. If I'm 2 feet from the hoop, if I'm 2 meters from the hoop, I have to throw it. I'm right under the basket, and I have to throw it at a very high angle, but not that hard. As I back up, my optimal angle becomes flatter and flatter. The next level of abstraction is that's if you shoot at 1.7 meters. What if I shoot at 1.2 meters from my chest? Or what if I shoot at 2.2 meters from above my head? Then the higher you are, the lower the optimal angle is. Interestingly enough, the optimal speed doesn't change that much. The point of this example is that, ultimately, all the information is in this last graph. These two graphs on the right tell you the story. I think it's very hard to explain this or understand it without building up. And notice how I use color here. You see, this is green. The green indicates that I'm indexing it by distance from the hoop. That's the green. Blue indexes the angle, and that's the blue. And then red indexes everything else. So with care, we can kind of explore our workflow and try to make the steps explicit that are otherwise implicit. I think you've seen a lot of graphs that you've made or other people have made where here's the answer and you don't see where it came from. I don't think people always reflect about where things come from. Okay, I have another example for you. Birthdays. So a few years ago, someone sent me this, sent me a paper that had been published. This is from, you see, it's from 2011. Influence of Valentine's Day and Halloween on birth timing. I think they sent it to me. So the idea was that Valentine's Day is a happy day, so people have more babies on Valentine's Day, and Halloween's scary, so people have fewer babies on Halloween. And someone sent it to me because I think they thought it was junk science and they wanted me to make fun of it for them. But actually, I thought it was pretty good. I'll show you the graph that they did. Here, so what they're doing is, here's on the left is Valentine's Day. You see the heart, right? And on the right, it's Halloween. You see the witch. Isn't that cute, right? They have the number of babies born. They had data from they had data of the total number of babies born every day for 11 straight years in the United States. It's like public information back when we used to have a government, and they would collect data and things like that. They had stuff like this. And here is the number of babies born on Valentine's Day and the week before and the week after. And similarly for Halloween, they break it into natural births, cesarean sections, and induced births. There are more babies born on Valentine's Day compared to the neighboring days. This looks like a real pattern to me. There are also fewer babies born on Halloween. This might seem weird to you that, it seems to make sense that, for example, induced births and cesarean sections, they could do more on Valentine's Day and fewer on Halloween, because if you get to pick, you might say, I'd rather not do it on Halloween, or you might say, why not do it on Valentine's Day? There's some flexibility. It might surprise you that there's a pattern for natural births also, but part of that is a selection effect, that if you suppose you didn't schedule your cesarean section the day before Valentine's Day, then the baby might just come out natural, or the induced birth the day before, the baby might come out naturally the next day. And conversely, if you scheduled the inducement for the day after, it may be that you don't need to induce because the baby's already born. And similarly in the other direction for Halloween. So even natural births can be affected because it represents births that weren't otherwise induced in some other way. So when I saw this, my first thought was that they're showing 30 days of data, and I want to see all 366 days of the year. So somebody made a picture for me. The number of births every day. So I just spend a minute with your neighbor talking about what patterns you see here. What are the most interesting patterns in this graph, and come up with some hypotheses of where they're coming from. Then we're going to do a little bit of statistical modeling. But spend a minute.
Yeah, well, why don't know that? That's all that I mean. That would make sense. I think you should look at like 90. Like see humans. Yeah, it's very less technical. But this is America. There's yeah, like China's intelligent. Yes, because that puts it's on the house that all means 9 I mean, they're very precise in sense. So yeah, that is actually. Yeah. No, why is very certain stuff very
Okay, so yeah, what's the wiggly thing happening for? Does anyone know?
Yeah. What?
Why is the graph wiggly like that?
For the weekends?
Yeah, well, it's data for 11 years. So yeah, the weekends. Yeah, so because it's not a full 28-year cycle, there is correlation between the day of the year and the week, whether it's weekday or weekend. So indeed. So this is the kind of thing, you don't just stare at data. Oh, and also you see Valentine's Day and you see Halloween, and it's not completely clear in this. Yes, Valentine's Day has more than neighboring days and Halloween has fewer, but there's other zigzags that are comparable in size. So we fit a statistical model, a decomposition, and this is, I'll get to that, sorry. But first, this graph, actually what happened was I wrote a blog entry about this and said, I'd like to see all the data. And somebody made this graph for me. I didn't make this graph. Just some rando made the graph and sent it to me. There's a red line, which is the average. There's also this blue curve, which is like uninteresting. It's some smoother. I don't care about that. And so then I posted this, and then somebody else sent me another visualization, which is this. Now, this is kind of a cool looking graph, but I hate it. In the sense that the most salient feature of this graph is that there are more birthdays in the summer. So you can see that much more clearly here. So it's more birthdays in the summer. So people are making the babies in the winter when presumably it's cold and they have nothing better to do, whatever. I know other than that, like I don't love this graph, partly because it's weird. Like it allows you to compare what happened on the 3rd of every month. You know, like you can see some things like here's July 4th, right? So it's not empty of information, but if I want to see July 4th, I'd really rather see July 4th here. I think this is much more clear. And that's because I'm graphing something quantitative. I'm graphing the number of babies. And this is giving me a qualitative comparison. It's not just interesting that July 4th is low, it's interesting that it's this much lower. And how does it compare to other things? So this allows me to make comparisons in a way that this doesn't. So I hate this graph. But then we made this. So this is a time series decomposition of the data. So the data started in 1968 and they went to 1988. And we decomposed the data into a slow trend. And the slow trend was just that there was a decrease in babies for a while and then a gradual increase as the population increased. A fast non-periodic component. So that fast component, the slow trend is like just big trends, like populations changing, people's tendency to have babies change just very slowly. There are baby booms and baby busts. The fast non-periodic component just corresponds to little things. Like there might be some bad news in the economy and fewer people get pregnant, or it could just be like different things happen in the news and it becomes more people decide to have a baby or decide not to. Sometimes when there are natural disasters, then even people who aren't living at those places, they're just in a less happy mood. Things happen. So it's non-periodic. Then we have the day of the week effect that you talked about. Fewer babies on the weekend because they don't schedule as many baby births on the weekend. If you look carefully, you can see that the day of the week effect increased over time. So it's flatter in 1972. When you get to 1988, it's bigger. And that makes sense. As in 1988, more births were being scheduled and having cesarean sections than had been in previous decades. There's a seasonal effect that we talked about. And finally, we have to estimate this day of year effect. And now it jumps out pretty well. Valentine's Day is positive. Valentine's Day is actually pretty much the only positive day of the year that we see. Well, you see July 4th, before and after July 4th, there are more babies. But that's because the baby has to come out sometime, right? If you're less likely to have the baby on the holiday, it has to happen before or after. Similarly with Thanksgiving, with Christmas, in the peak before and the peak after Christmas isn't so much that people want to be born they want their babies to be born on the 27th. It's just if you can't be born on Christmas and you can't be born on New Year's, there just aren't that many places that you can go. So you get this pattern. We fit the data again. This is from 1968 to 1988. We fit the data to a new data set. And there's a reason why I'm showing you this. So this is similar. There's the slow trend, the fast period, non-periodic. The day of the week effect is bigger, which is correct. It's larger than it used to be. It's no longer really changing over time. We've stabilized. The seasonal effect is kind of moderate. So look at this. The earlier there is a larger seasonal effect. It was doing all these things. Now the seasonal effect is smoother. That's sort of an artifact of our fitting procedure. And I want you to look at the day of the week effects for a second. Look at the period. Do you see actually, is this after 2000? So now there's a 9/11 effect that wasn't there before. But look at late September. Do you see that there's a positive day of year effect for all of late September? But that can't be. Like you can't hold your baby in for 3 weeks. right? So this late September effect, this is an artifact of our statistical modeling procedure. Because really, and here, the same thing on Thanksgiving week. You can't really have a week with that many fewer babies. So what's happening here with the day of the week effect being consistently positive in the second half of September, that's really a seasonal effect. The model is mistakenly, it's over smoothing this and putting it in the wrong place. And we can see this because what we did here is we fit 366 day of year effects, which were little spikes, which could be positive or negative. And that's really wrong. What we really should be fitting is a model with ringing, where ringing means like what's happening around Christmas. So instead of fitting a spike, you should be fitting a set of functions that go down and then up and then down and then up and have an integral of 0. Because these represent shifting of when the babies are born. It's through this graph and through my exploration of my expectations that I realized that our model was lacking in this way. But even an imperfect model can show you some stuff. So I'm going to show you one more graph. This is the same as the last day of year effect, but I'm going to blow it up. And what we did was we circled the 13th day of each month. But look at that. This was there all along in the data, but we hadn't noticed. But when you circle it, it just jumps out at you that the people are avoiding having babies on the 13th. Now, the funny thing is, this was here. Look at 13. I just didn't think of looking at it. So this graph that I hated actually provided information. This is not the best graph of the data, but it provided one piece of information that you wouldn't have otherwise seen. It was later someone suggested we look at the 13th, and we did this. So it's kind of amazing how much can be in your data that it's in front of your face and you don't even notice. It's kind of stunning in that way.
Can you explain a little bit more what certainties is very special?
Wait, what did you say? You have to repeat it.
Can you explain a little bit more why certainties is special and people want to avoid that?
Oh, he just wants to understand why the 13th.
Oh, why the 13th? It's considered to be bad luck.
Yeah.
So people have the option. Yeah.
Oh, sorry, I'm Asian, sorry.
Yeah, I mean, presumably being born on New Year is not considered bad luck. It's just that they don't schedule things on New Year's. Christmas, maybe people don't want to be born on Christmas. Like the last thing you need is to have your birthday overwhelmed by the national holiday. But I think most people don't want to be their kid to be born on April Fools, right? Like there are things like that. But a lot of it, I think, is just convenience. But the 13th is just people don't want it. You also have a little flexibility. If their baby's born at 11 at night, they might, and you ask them to say the birth is the next day, I think they'll do it for you. There's
data from the United States. So have you looked at the data from other countries, whether it's the same?
You have to repeat the question.
He's asking if this data is from the United States and if
Yes.
you've looked at data from other countries.
We have not, but other people have. And you see other patterns in other countries. But yeah, it's all doable. We have this example. Well, we use it in our Bayesian data analysis book, but then we reanalyze the data for our new Bayesian workflow book, which isn't finished yet, so that'll have all the code. So then you can throw other birth series. You don't have a lot of series like this, but there is some. Now I got more stories, but I think maybe I'm out of time at this point. And I think I've given my messages pretty clearly. So do you have any, I could tell you more stories, but I'd be happy to, answer questions or whatever.
Anybody have any questions?
It could be about anything. It does not have to be about these examples.
Do you think this kind of Bayesian method and statistics will work in the age of machine learning and deep models? Because they really use some very deep models to analyze data. So what is the advantage of using Bayesian model in this time?
Well, I made this pretty graph, so that was good. I think that a lot of the most important problems we work on are not about analyzing the data, but about learning about latent structure. So for example, if I'm designing a drug and if I'm working on a drug design and I want to figure out a good dose, then I have a model for what's happening inside the body. And that has latent parameters for the concentration of the drug in different organs. And there's a differential equation model you can use to track that. You can, like from there, you can fit a model to data and estimate these things. And I think it would be, I mean, I'm sure there's always other ways of doing things, but we use Bayesian methods because we can then model these latent quantities like the dose inside your body. We use Bayesian methods when we have sparse data. So when we're doing election forecasting, we don't have a lot of elections. And so the goal is like you kind of have to build a model. So if I have information like if there's a swing in Ohio, there will probably be a comparable swing in Pennsylvania and Michigan. That's the kind of thing that I can incorporate into a model. And that seems to work pretty well. So those are like the sorts of examples that we work on where it seems to make a difference.
So I actually have a quick question. So I know, like I've read some of your work. I know you're very critical of like p-values in statistics and how they can come across as disingenuous. I was wondering if you could talk shortly a little bit about that.
So there was a study done a few years ago of heart stents. It was a certain procedure for if people are having difficulty breathing, was to put this thing inside people's arteries, and it was a treatment that was sometimes done on people, and it wasn't clear how effective it was. So they did an unusual experiment where it was a randomized experiment where half the patients got this heart stent, which requires an actual operation to install into your heart. And then half the people got what's called a sham operation, which means they opened up their chest and did nothing. Well, they don't do that kind of, I mean, they don't approve that kind of study unless it's considered important. But they did it. So they did the big study, and the outcome was treadmill time. So the people in the study had an average treadmill time of about 500 seconds with a standard deviation of about 100. So most people between 400. I'm sure all of you and most of you in the room could probably do like, go indefinitely on the treadmill. But these are heart patients, and they could go about 500 seconds before that was it. They powered the experiment so that if the treatment had an effect of 30 seconds on treadmill time, that it would be almost certainly statistically significant result. They did the experiment. The estimated effect was 16 seconds, and the p-value was 0.2. Not statistically significant. The 95% interval included 0. This was reported in the newspaper as here, I'll turn off the slides. Stop staring at this. This was reported in the newspaper as stents have no effect. Great surprise. People thought it was effective, and it wasn't. Right? But they didn't have to. They could have said we report that there was an effect of this much. It was half as much as was expected, maybe. But there's uncertainty. It turns out they didn't do the best analysis. So I looked at the paper and I saw that they did not correctly adjust for the pre-treatment treadmill time. After you do the adjustment, the estimate goes up from 16 seconds to 21 seconds, and the standard error goes down. I was really excited. I was picturing this like headline in the newspaper, like statistician saves the day, new analysis. Well, the new analysis had the p-value went from 0.2 to 0.09. So it still wasn't, I was really bummed because if it was 0.04, I would have been like would have been like a victory, right? Still not statistically significant. Well, the estimates, data are basically consistent. The treatment effect, the average effect is probably between 0 and 30 seconds. It's probably positive effect, not as high as they might have wanted it to be. No, that's how I think it's the right way to report it. So it's awkward because I don't have a slick answer. I'm not saying, well, take away p-value, do this instead. I'm saying that you actually have to put a little bit more thought into it and acknowledge the uncertainty. But that's kind of what I would recommend.
Okay, thank you. I think we have time for one more question. Yeah, what?
Where can I find your blog?
You want to know where you can find your blog?
Yeah, if you Google like my name blog, you'll find it, So yeah.
You have one last question.
So my work recently involves evidence lower bound. I think it's also related to Bayesian's method, right? So is your work related to evidence lower bound, and what is your opinion about that?
Yeah, I think, it's related. You take a look at chapter 7 of Bayesian data analysis. We talk about, my colleague Aki Vetteri and I work, and it's related. We do this leave one out cross validation, and it's kind of related to that. I don't really like the term evidence. It's a kind of weird term because it's actually just, it's a marginal likelihood. It's not, I don't know. It's not really evidence, but anyway, when it comes to computation, it comes up in some of the variational methods we use. But when you want to think about in terms of statistical theory, I recommend there's that. And also we have some papers. If you go to my webpage under published papers, we have some papers on stacking, which is predictive model averaging. And that's kind of related too. It's not exactly what you're doing, but I don't want to refer you to something that's already what you're doing. This is stuff that's a little different, but has some connection.
So, general opinion about generating model and evidence lower bound used in generating model.
Well, I think generative models are good. They represent a story about the world. So I'm a big believer in setting up a model and then seeing where it doesn't work. And then when your model is not working well, then that is motivation to improve it. So I think I'm through the golf example. The birthdays example is a good one where we set up a model and we put a lot of work into it and it wasn't perfect, but that allowed us to move forward. And you can definitely use different measures of fit. Like we prefer leave one out cross validation, but you can use these measures of evidence or whatever to assess model fit. But I think the goal is ultimately to, at least for me, the goal is to have some mapping which allows me to make generalizations.